Well, we're going to start chapter 8 today, and it has applications to the COVID-19 virus, interestingly enough. We'll say that a differential equation, that's the topic of the chapter, is an equation for some function y of t, dependent variable of an independent variable, involving one or more derivatives of y. Such as a function of t, y, y prime through y n minus 1 means n minus first derivative of y. We can't make n minus 1 hash marks there. Equals 0. This is an arbitrary equation involving t, y, and some of the derivatives. If it involves at least one derivative of y, then we call it a differential equation. We'll say it is nth order if n, let's say this goes up to nth derivative here. We'll say this is the nth derivative of y. If yn is the highest derivative that appears. Now, differential equations in general tend to have an infinite number of solutions in practice. For example, this one. Y double prime plus 4y equals 0. How can we test if something's a solution? A solution of a differential equation, I'll write DE for short, long pair of words, is a function y of t that satisfies the equation, that's all. For instance, suppose I consider y1 of t equals sine of 2t. Is that a solution to this differential equation? You can test it just by taking its derivatives and plug it in. This is a second order differential equation, because the highest derivative is the second derivative. Now, if you take this function, its first derivative is the cosine, twice the cosine, right? Derivative of sine kt is k cosine kt, you'll recall. Let me fix this. And then the second derivative is the derivative of 2 cosine 2t is minus 4 sine 2t. When you plug this in, for y double prime you have minus 4 sine 2t. When you plug in for y, you get sine 2t. And you plug in the function and its second derivative on the left, and what do you get? Minus 4 sine 2t plus 4 sine t equals 0. Sure enough, it satisfies the equation, so sine 2t is a solution. But it's not the only solution. So some of the problems just say, see if this is a solution, all you have to do is calculate its derivatives and plug in. similarly, y2 of t equals cosine 2t has first derivative minus 2 sine 2t, second derivative minus 2 cosine 2t, and you plug in on the left y double prime, oops, this is minus 4, sorry. And you get minus 4 cosine 2t plus 4 times, plug in y cosine 2t. Well, minus 4 cosine t plus 4 cosine 2t is 0. Sure enough, cosine 2t is also a solution. And in fact, you can show in differential equations class that any function c1 cosine 2t plus c2 sine 2t is a solution. You can plug this in with arbitrary constants in it. So if you take c1y1 plus c2y2, this is a solution. So you take the derivative and you get minus 2 c1 sine 2t plus 2 c2 cosine 2t. If you take the second derivative, you got minus 4 cosine 2t minus 4 sine 2t, and you can plug this in for y double prime and get minus 4 cosine minus 4 sine, and then add 4 times y, which is cosine, I forgot my c1s here, c1 and c2, forgot my c1 and c2, plus 4 cosine, c1 cosine cosine 2t plus c2 sine 2t, and you see that these all cancel out. This one cancels this one cancels this one, and you get 0. Any function of this form is in fact a solution. These things tend to have an infinite number of solutions in general. But that's how you test to see something's a solution. Just plug it in and see. And it may have an arbitrary constant and still be a solution. Here's a very simple example. Suppose I had y prime equals 2.6y. You've heard that each person on the COVID virus infects about 2.6 others, right, in one time period. Maybe it's a few days, right? And so the unit of time is a few days or so. Y prime equals 2.6y. How can I solve this? Well, I will rewrite this actually as dy dt just for purposes of making this look a little easier. I can divide through by y and write this as 1 over y dy dt equals 2.6, and then I can integrate both sides with respect to t. And what I get on the left, well, by u substitution, if I or y substitution, I make dy dt dt is equal to dy, and I can rewrite this as integral 1 over y dy equals integral of 2.6 dt is 2.6t, and then there's an integration constant. What I get on the left is ln absolute value of y equals 2.6t plus an arbitrary constant. There's the solution to the spread of COVID-19 problem. And if I take the exponential of both sides, now I've got absolute value of y equals e to the 2.6t plus a constant, or if you like, absolute value of y equals e to the c times e to the 2.6t. And this says that y is equal to plus or minus e to the c, e to the 2.6t. There's what we call it, well, almost the general solution. There's one more thing. When I divided through by y, I assumed y equals 0 wasn't a solution. If you go back and check by plugging in, derivative of 0 is 0, the right-hand side is 0. 0 is a solution. So not only is e plus or minus any constant times e to the 2.6t a solution, the general solution, when you include the y equals 0 solution that we previously omitted, is y equals an arbitrary constant, we'll call it a, where a is plus or minus e to the arbitrary constant c, or 0, a e to the 2.6t. There's the general solution to this differential equation. It points out that we haven't got how many people get infected by the COVID virus. We've only got a general solution. What's missing here that we get the exact number of people that are infected, right? Well, in practice, what people like to do is give, instead of a differential equation by itself, a differential equation with values for y and its first n minus 1 derivatives for an nth order equation. So we'll say an nth order initial value problem to try and get a unique solution. And we'll abbreviate that IVD, is a differential equation dE of nth order. Means it has derivatives through n with n initial values. Usually given at t equals 0, but they could be at some other value. So we'll say y at t0 is equal to some number we'll call y0. At some time you have this many infected or something. Y prime of t0 is equal to y0 prime, and so on. We want the n minus first derivative at t0 equal to y0 n minus first derivative. So this is a number on the right. The n minus 1 doesn't indicate derivative here. It's just notation for the number that is the n minus first derivative at t0. So on the right are all numbers, and on the left are y and its derivatives evaluated at t0. So that's an initial value problem of nth order. It's an nth order differential equation with initial values for y and its first n minus 1 derivatives. Let's go back to the problem we had. Now, consider the differential equation dy dt equals, equals 2.6y together with an initial value. Since it's a first order equation, I only need one initial value. Y at time 0, let's say, is 100 people. Initially you start with 100 people. And how many become infected if each person infects 2.6 others in some time period, and they infect 2.6 others and 2.6 others. You get this kind of a growth model that the rate of increase of the infected is proportional to the number of people currently infected times 2.6. So we already know that the general solution of the differential equation is y equals a e to the 2.6t. And now we apply the initial value that when t equals 0, y equals 100. That's what the initial value says. And we get 100 equals a e to the 2.6 times 0. Well, e to the 0 is equal to 1. So a equals 100. And we get a unique initial value problem solution. That's the purpose of the initial value. That y is equal to 100 e to the 2.6 t. If you check this out, this is a pretty quick growing, pretty fast growing function. And that's why you get so many people getting sick so quickly. All right, so there's a solution to a very simplistic model. What happens in practice, actually, is that this doesn't keep growing forever. What we eventually get to is the point where you can't infect so many people because so many people are already immune, and then the equation ceases to increase exponentially like this, or the solution ceases to increase exponentially like this. Now let's consider a harder initial value problem. Oops. Suppose somebody gives you this problem, y double prime plus 3y prime plus 2y equals 0. You could plug in actually in higher order differential equations, find out that the general solution is, you're not expected to derive it in this class, but it turns out that the general solution, the form of all solutions, is y equals c1 e to the minus t plus c2 e to the minus 2t. That's an infinite number of solutions. This comes out that in order to solve a second order equation, you have to do two integrations. It gives you two arbitrary integration constants. Like the last problem, we got one arbitrary integration constant, so we needed one initial value. This one will integrate twice, get two arbitrary constants, so we'll need two initial values. So two initial values for a second order equation. Suppose I said that in addition to this, I'm given initial values y of 0 equals 2, and y prime of 0 equals minus 3. What is the unique solution to this second order equation with two initial values? Well, we just plug them both in, right? The first one says when t equals 0, y equals 2, and so we put 2 in for y, times c1 e to the 0 plus c2 e to the 0 says that c1 plus c2 equals 2. Then we need to calculate y prime. Let's do it over here on the side. Y prime, the derivative e to the minus t is minus e to the minus t, so y prime is minus c1 e to the minus t. Derivative e to the minus 2t is minus 2 e to the minus 2t. So this is minus 2 c2 e to the minus 2t. There's the derivative. And the second initial condition says that when t equals 0, y prime is minus 3. So we put that into the derivative equation and get minus 3 equals c1 e to the 0 minus 2 c2 e to the 0, or more succinctly, I guess, c1 minus 2 c2 equals negative 3. How about that? Now what this does is it gives us two linear equations for two unknowns, c1 and c2, and we can solve these and we'll get a unique solution. So a second order equation gets two initial values, one for y and one for y prime at the same value of t. And here's the system of equations. How can we solve that? Well, a nice way is to write them in this form. c1 plus c2 equals 2. Put the like numbers c1 and c2 over each other. c1 minus 2 c2 equals negative 3. Call it equation 1 and equation 2. And we could add a multiple of one equation to another, right? Suppose we take the first one minus the second one to eliminate c2. So if I take 1 minus 2, what do I get? c1 minus c1 is 0. c1 minus a minus 2c2 is 3c2. Equals this one minus this one is 2 plus 3 is 5. Tells you that c2 equals 5/3. Evidently there's a unique solution. Oops. We have to this, that y equals c C1, oh, I didn't finish finding C1. Now you can plug 5/3 into either equation to get C1. If C2 is 5/3 and C1 plus C2 equals 2, that tells you that C1 is 1/3. 5/3 plus 1/3 is 2. Alright, so now I deduce, putting these in, that y equals C1, 1/3 e to the minus t, plus C2, 5/3 e to the minus 2t. There's the unique initial value problem solution. Try section 8.1 homeworks that I'm sending in the email here and see if you can do all these problems now. In addition to this, I want to start 8.2 this lecture. And in 8.2, we consider a particular type of equation that comes up quite a lot called a separable equation. A separable equation, here they'll use x for the independent variable, so y is a function of x. dy dx equals a function of x and function of y. If it can be written in this form, a function of y alone times dy dx equals a function of x alone, then we say the equation is separable, because if we just multiply both sides by dx and integrate like we did on that other problem, we have m of x dx, only x and dx on the left, and n of y dy, only y and dy on the left. We can integrate both sides. Integral n of y dy dx equals integral m of x dx. And this, by the substitution theorem, dy dx dx is dy. Here it's written as the u substitution theorem. U equals y of x. Integral n of u du equals integral m of x dx. And by integrating, we then get all the solutions to the differential equation. Let's try it on this one here, whose solution I'll put out. Oops. Suppose I wanted to solve dy dx equals 6y squared x, together with an initial value, otherwise I'll get an infinite number of solutions. Y when x equals 1 is 1/25. Alright? So what do? I separate variables. I'll divide by y squared and I'll multiply by dx. So I get y to the minus 2 dy equals 6x dx. Now I integrate both sides, because dy can be written as dy dx dx, and then use substitution. So this is integral y to the minus 2 dy equals integral 6x dx. Integral y to the minus 2 is minus y to the minus 1. Integral 6x is 3x squared plus a constant from the integrations. Gives us, this is the general solution set. I just have to solve for y. And what I'll do is, before I do that, I'll plug in the initial value. I'll plug in that y equals 1/25 when x, y is equal to 25, 1/25 when x equals 1. And that determines that c is equal to minus 28. Consequently, I can put that in the equation, get minus 1 over y is 3x squared minus 28. So there's how the initial value determines the integration constant. Now I solve for y and get y equals 1 over 28 minus 3x squared. There's how to solve an initial value problem when it's a first order separable equation. You simply separate the y with dy on one side, x with dx on the other side, slap an integration sign on each side that's equivalent to a u substitution, plug in the initial value after integrating, and you get the unique solution, generally unique solution to your initial value problem. Here's another problem. Suppose I have y prime equals this quotient. What a mess. Well, I can still separate variables. I multiply by 2y plus 2y minus 4 and multiply across by the x, and I get 2y minus 4 dy equals 3x squared plus 4x minus 4 dx. X's and y's are separated each side, so I can slap an integral sign on there. When I integrate this side, I get y squared minus 4y plus an arbitrary constant. I'll put them both on this side. Integrate this side, I get x cubed plus 2x squared minus 4x plus c. Now, I also have the initial value, y of 1 equals 3, so I can plug in that when x equals 1, y equals 3 in this equation, so I plug in 3 for y in each of the spots and 1 for x in each of the spots. That determines that c has to be negative 2. I infer that my solutions are y squared minus 4y equals x squared, x cubed plus 2x squared plus minus 4x minus 2. Well, this is technically not a solution to the differential equation. Right? A solution is y a function of x that satisfies the equation at each point. So I have to solve this for y. Well, I can use the quadratic formula. I'll put this over on the left and think of this as ay squared plus by plus c equals 0. If I apply the quadratic formula, minus b plus or minus square root b squared minus 4ac all over 2a, I get this solution. Now I've got a solution for y as a function of x. Oh, there's a plus or minus. Why is that there? Well, what happens is it turns out that both of these are solutions. You can put the plus sign in or the minus sign in, and you get a solution, y as a function of x. All right, we'll try the problems on separable equations, and send me any questions you have.